math, walang maiiwan. Math-sayang Math-aral tayo ng Math-tuto, upang ika'y umasenso. Maging matyaga, maging matalino, halina Math-aral na tayo. Maging matyaga, maging matalino, halina Math-aral na tayo. Halina Math-aral na tayo. Halina Math-aral na tayo. Halina, 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 aral na tayo.
Hello at magandang buhay, parents, teachers, and students. Welcome to our Project SOAR, a series of online academic review on mathematics CLAID Modules. I am Mrs. Joana Grace B. Lara from Andres Bonifacio Integrated School, and I will be your teacher reviewer for this week 6 of quarter 4 in grade 8 mathematics. In this week 6 of quarter 4, we will discuss about probability of simple event and theoretical and experimental probability. These are the objectives of our lesson today. 1. Finds the probability of a simple event. 2. Illustrates an experimental probability and a theoretical probability. And lastly, solves problems involving probabilities of simple events. We will have first a review before we proceed to our lesson. Let's answer this review. Direction: complete the sample space tree diagram for the experiment that consists of tossing a coin 3 times. So we will fill in the circles here. So we will toss a coin. For the first toss, we have 2 outcomes. We have the tail and the head. For the second toss, we have the head, tail, and head and tail. And for the third toss, so we have head, tail, head, tail, head, tail, head, and tail. So these are the sample space tree diagram for tossing a coin 3 times. Let us list down the sample space of our given experiment. We have tail, head, head, tail, head, tail, 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 head, tail, 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 head, 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 tail, head, tail, head, head, tail, tail. So the total sample space is 8. Now, let's proceed to our first lesson, which is all about probability of simple event. Probability of simple event. The probability of an event is the ratio of number of possible outcomes in the event to the number of all outcomes in the sample space. In symbols, we have P, or probability of an event, is equal to n plus open parenthesis e, which is the number of event, over n plus open parenthesis s, which is the number of sample space. Example: suppose we roll a standard 6-sided die 1 time. We will answer the following questions. A. What is the probability of getting a number greater than 4? B. What is the probability of getting an even number? Here's our solution. Our sample space in rolling a die are 1, 2, 3, 4, 5, and 6. When we say sample space again, these are all possible outcomes. So we will let A be the event that we get a number greater than 4, and let B be the event that an even number occurs. So the total outcomes that we get a number greater than 4 in rolling a die are 5 and 6. So the total number of an event A is 2. The possible outcomes of event that an even number occurs are 2, 4, and 6. So the total number of event B is 3. Our sample space are 1, 2, 3, 4, 5, and 6. So the total number of sample space is 6.
Letter A. What is the probability of getting a number greater than 4? So there are 6 possible outcomes, or this is the sample space. We have 1, 2, 3, 4, 5, and 6. So only 2 outcomes correspond to getting a number greater than 4. So which are 5 and 6. To get its probability of event A is equal to the number of event over the number of sample space. So the number of event or the outcomes corresponds to getting number greater than 4 is 2 over the number of sample space of it is 6, or in simplified form this is 1/3. Therefore, the probability of getting a number greater than 4 is 1/3 or 0.33 or 33%. Letter B. What is the probability of getting an even number? A total of 3 outcomes corresponds to getting an even number. These are 2, 4, or 6. To get its probability, the number of event which is 3 outcomes correspond to getting an even number over the number of sample space which is 6. In simplified form, we have 1/2. Therefore, the probability of getting an even number is 1/2 or 0.50 or 50%.
I hope you understand on how to get the probability of simple event. Now let's proceed to our next lesson, which is all about experimental and theoretical probability. Let us discuss first experimental probability. Experimental probability. This is also known as empirical probability. It is based on actual experiments or adequate recordings of happening of events. When an experiment is performed that consists of certain number of trials, the experiment probability of an event E is given by probability of event is equal to the number of trials where A occurs divided by the total number of trials. Example number 1. The bar graph shows how adults in a survey would choose to be if they could choose any age. Find the experimental probability that a randomly selected adult would prefer to be at least 40 years old. So as we can see in our bar graph, there are 463 adults who choose under 20 years old. There are 1,085 who choose to be 20 to 29 years old. And there are 879 adults who choose to be 30 to 39 years old. There are 551 adults who choose to be 40 to 49 years old. There are 300 adults who prefer 50 to 59 years old. And lastly, there are 238 adults who also prefer 60 to 69 years old. This is our solution for example number 1. The total number of people surveyed is 3,516. We add up the number of adults who answered the survey. Of those surveyed, 1,089 would prefer to be at least 40. So we add the adults who choose to be 40 to 69 years old. So getting the probability of adults who at least 40 or who choose to be at least 40 years old is equal to 1,089, which this is the number of event, and 3 over 3,516, which is our sample space. So we have estimating to 0.310 or 31%. Example number 2. The table shows the result of spinner experiment. We will find the experimental probability of A4. In our table, number 1 occurred 6 times. Number 2 occurred 11 times. 3 occurred 19 times. And 4 occurred 14 times. So the total number of trials is 50. So, the outcome of 4 occurred 14 times out of 50 trials. To get the probability of spinning a 4, so 14, this is the number of trial where 4 occurred over 50, which is the total number of occurrences. We simplified it, it becomes 7 over 25 or 0.28 or 28%. Therefore, the probability of spinning a 4 is 28%. Let's proceed now with theoretical probability. Theoretical probability is probability that is determined based on reasoning. To find the probability of an event, which is also called likelihood of an event, use the formula below. Probability of an event is equal to the number of favorable outcomes divided by the number of possible outcomes. Let's have this example. Suppose we roll a standard 6-sided die one time. Letter A. What is the probability of getting a number less than 5? Letter B. What is the probability of getting an odd number? Let us answer letter A question. What is the probability of getting a number less than 5? The number of favorable outcomes is 4. We have 1, 2, 3, and 4. The number of possible outcomes is 6. We have 1, 2, 3, 4, 5, and 6. Therefore, the probability of getting a number less than 5, which is computed using the formula number of favorable outcome divided by number of possible outcomes, we have 4 over 6. 4 is the number of favorable outcome. 6 is the number of possible outcome. Getting its simplified form, we have 2/3 or 0.666 or 0.67. In percentage, we have 67%. Therefore, the probability of getting a number less than 5 is 67%. Let's have letter B. What is the probability of getting an odd number? The number of favorable outcomes is 3. From the 6-sided die, the odd numbers are 1, 3, and 5. The number of possible outcomes is 6. We have 1, 2, 3, 4, 5, and 6. Therefore, getting the probability of an odd number when we roll a standard 6-sided die is 3 over 6. 3 is the number of favorable outcomes and 6 is the number of possible outcomes. Getting its simplified form, we have 1/2 or 0.50 or 50%. So we can say that the probability of getting an odd number when we roll a standard 6-sided die one time is 50%. Take note that probability of simple event is one of the examples of theoretical probability. Let us check your understanding by answering this activity. For this activity, you will need 2 coins. First, you will determine the theoretical probability of events. Then, you will flip the coins 100 times and determine the experimental probability of the events. I have here the results of flipping 2 coins 100 times. We have 2 heads, 23 times occurred, 2 tails, 30 times occurred, 1 head and 1 tail, 47 times occurred, and the total number of trials is 100. Using the result of the experiment, we will answer the following question. Number 1. What is the theoretical probability that a coin toss results in 2 heads showing? Number 2. What is the experimental probability that a coin toss results in 2 heads showing? Number 3. What is the theoretical probability that a coin toss results in 2 tails showing? 4. What is the experimental probability that a coin toss results in 2 tails showing? 5. What is the theoretical probability that a coin toss results in 1 head and 1 tail showing? 6. What is the experimental probability that a coin toss results in 1 head and 1 tail showing? And lastly, compare the theoretical probabilities to your experimental probabilities. Why might there be a difference? Let us answer the first 2 questions. Number 1. What is the theoretical probability that a coin toss results in 2 heads showing? So, the possible outcomes are head-head, head-tail, tail-head, and tail-tail. So, we have 4 possible outcomes. While we have 1 favorable outcome, which is head-head. What do you think the theoretical probability of 2 heads showing? Yes, the probability of 2 heads showing is 1/4 or 0.25 or 25%. Number 2. What is the experimental probability that a coin toss results in 2 heads showing? So based on our experiment that we had, 2 heads occurred 23 times, 2 tails occurred 30 times, 1 head and 1 tail occurred 47 times, and the total number of trials is 100. What do you think is the experimental probability of 2 heads showing? Very good. The probability of 2 heads showing is 23/100 or 0.23 or 23%. Let's proceed with number 3 and number 4 questions. Number 3. What is the theoretical probability that a coin toss results in 2 tails showing? The possible outcomes are head-head, head-tail, tail-head, and tail-tail. So we have 4 possible outcomes. And we have 1 favorable outcome, which is the tail-tail. What do you think is the theoretical probability of having 2 tails showing? Yes, that's correct. The probability of 2 tails showing is 1/4 or 0.25 or 25%. Number 4. What is the experimental probability that a coin toss results in 2 tails showing? So these are the result of flipping 2 coins 100 times. What do you think is the experimental probability of 2 tails showing? Very good. The probability or the experimental probability of 2 tails showing is 30/100. In simplified form, we have 3/10 or 0.30 or 30%. Let's have the 5th and 6th question. Again, we have 4 possible outcomes. We have the head-head, head-tail, tail-head, and tail-tail. And this time, we have 2 favorable outcomes, which are head-tail and tail-head. What do you think is the theoretical probability that a coin toss results in 1 head and 1 tail showing? You're absolutely correct. The probability of 1 head and 1 tail showing is 2/4 or 1/2 or 0.50 or 50%. Number 6. So we will get the experimental probability of 1 head and 1 tail showing. So these are the result of flipping 2 coins 100 times. What do you think is the experimental probability?
You are so great! The probability of one head and one tail showing is 47 over 100 or 0.47 or 47%. Last number. Compare the theoretical probabilities to experimental probabilities. Why might there be a difference? Using the table, as a result of their theoretical probability and experimental probability, two heads showing having 25% of theoretical probability and 23% in their experimental probability. We have negative 2% error. Two tails showing the probability or theoretical probability of it is 25% and the experimental probability of it is 30%. We have negative 5% error. And one head and one tail showing its theoretical probability is 50%, while its experimental probability is 47%. We have 3% error. Remember that as the number of trials increases to infinity, the experimental probability shall become very close to the theoretical probability, and this is the law of large numbers. I hope you learned a lot today. Thank you for watching. If you have some questions, feel free to send us a message in our official Facebook page, Math Team, Mathematics Teachers Association of Mandaluyong. I am Mrs. Lara saying, Math-sayang Math-aral, tayo ng Math-tuto.